Good morning, everybody.
Good morning.
Good
Good
morning.
morning. I want to make sure you are seeing my note.
Yes.
See my okay, very good. Let me quickly mark the attendance for today. Kaida's here, Michael's here, Max is here. Very good. Jose, I don't see him. Jose, are you here? Is Alisa Haley's here? Eliza is here. Bailey's here. Okay, awesome. 6 participants. This is my note. Last class, we covered most of the thing about complex number, right? We have some, I think the division of a complex number, we didn't really practice enough. So we are going to do more practice about the division of complex numbers. Let's look at the Luhmann question number 21. I think Luhmann question number 21 is not about division. 12 to 14. So let's find a problem there. Two point one. Number 12, number 13, number 14 are about the division of complex numbers. Let's look at number 12. I'm going to put it here. The last question of last class, we covered 6 plus I divided by 4 minus 3i. If the divisor has both real part and imaginary part, we need to multiply both numerator and the denominator by the conjugate of the denominator. What if in the division of two complex numbers, the divisor, the number in the denominator, do not have the real part? For example, this expression, numerator -4 plus 2i, denominator 7i. The complex number in the denominator is missing the real part. It only have an imaginary part multiplied with the imaginary unit. Then how do we process this division? So in this case, if you follow the rule we had for the previous problem, it will still work. But a more convenient method is to simply multiply both numerator and the denominator by I. Multiply numerator by I, multiply denominator by I. Technically, I mean, not technically. So if we follow the rule, when we divide the two complex numbers, we should multiply both numerator and the denominator by the conjugate of the denominator, right? The denominator is 7i, which is 0 plus 7i. The conjugate is 0 minus 7i. So negative 7i is the conjugate we're supposed to multiply, right? But, you know, you will find out is the negative 7 actually really not necessary. When the denominator does not have the real part, all we need to do is to multiply both numerator and the denominator by the imaginary unit. Let's see what happened after we multiply the top and the bottom by the imaginary unit. If you like I in front of the parentheses and should feel better that way when you apply the distributive property, please do so. We can write I in front of the parentheses, 94 plus 2i. If we distribute, we multiply I with both terms in the parentheses, I times 94 plus I times 2i. And let's see what we have. I times 94 gives 94i. I times 2i gives us 2i squared. Yeah, I'm going to put it here. And later, we'll keep simplifying the numerator. The denominator, 7i times I, that is 7i squared. And we know I squared is -1. And that is -7, right? Okay, so we can keep going here. Numerator, negative 4i plus 2i squared. I squared is equal to -1. So 2i squared is -2. Okay, 2i squared is -2. So the numerator is -4i minus 2. And we can rewrite the numerator as 92 minus 4i. 92 minus 4i. Denominator is 97. I don't know if I mentioned the Mickey Mouse structure, left ear, right ear, and head, right? When all the three parts have a common factor, we can get rid of the common factor. As you can see, left ear, negative, right ear, negative, the head, negative. If all the three parts are negative, we could just change them all to positive, right? So 2 plus 4i over 7. 2 plus 4i over 7. And then we use the first part in the numerator divided by the denominator. We have 2 over 7 and then plus 4 over 7 times I. And rewrite the result. The result is a complex number. Rewrite it in the standard form. Real part plus imaginary part times I. So that's how do we divide two. That's how do we process the division of two complex numbers when the denominator, when the divisor is missing the real part. You do not need to find a conjugate. Instead, you only need to multiply both top and bottom by I. You'll be good. All right. Practice more. We have the class recorded last time. We covered this problem, 6 plus I all over 4 minus 3i. When the denominator has the real part, also imaginary part, and you identify the conjugate of the denominator and multiply both top and bottom by the conjugate. And the denominator 4 minus 3i times 4 plus 3i, you can use the formula we proved last class. If we have two complex numbers, they are conjugate of each other, then the two complex numbers multiply to a real non-imaginary real number. Is a real number without I. Is a squared plus b squared. A is the real part. B is the imaginary part. I hope you spend a little bit more time on this formula. Formulas are our tools. The more tools you have, the more efficient you will become when you solve problems. All right, so I think that's pretty much everything about complex numbers. I have number 4 here, gives the expansion of the number system. I can quickly explain that. The number system develops over time in the history. The very beginning, our ancestors only know about whole numbers. Whole numbers include a zero. Actually, my bad. We start from natural number. It's from natural number. Natural numbers. Well, we're just guessing. Our ancestors, they probably will not, probably doesn't know zero the very beginning, right? They might start from 1, 2, 3, and so on. As they go hunting, they kill the rabbit, so that is 1. If they kill the 3 deers, that is 3, right? And they use those natural numbers. And then what if one day they didn't catch anything? And that is 0. But 0 is not a natural number. With 0, we add a 0 to the set of natural numbers, we get a whole number set. Whole number. Whole numbers include 0, 1, 2, 3, and so on. All right? And maybe over time, then they notice if they, over many days, they don't have anything to eat, they would have to borrow from their neighbors, right? Maybe another tribe, and they owe a deer or owe a rabbit to their neighbors. And how do they record that? They need a negative, right? So the number system was expanded to integer number set. Integer number set. And integers include 0, positive 1, negative 1, positive 2, negative 2, positive 3, negative 3, positive 4, negative 4. In other words, all the whole numbers and their opposites. And one day they notice, let's say they make a cake. Let's say they had a cake at that time, and they didn't finish the cake. They have to cut the cake into pieces and share the cake with some other people. They developed the idea of fractions, right? With fractions, then the number of integer, then the number system integers is not enough to handle the situation. So they again expand the number system to rational number set. Rational numbers. Rational numbers, the formal definition for rational number is anything that can be written in this form. P and Q are integers. Simply put, you can understand rational numbers as fractions, or anything that can be written as fractions. You might wonder, is a 5 a fraction? Technically, yes, you can write 5 as 5 or 1, right? Anything that can be written as an integer over an integer is a rational number. 5, yes, is a rational number because you can write it as a 5 or 1, right? Or negative 2 over 3. Yeah, those are rational numbers. And one day, people found out there are numbers, they are not rational numbers. For example, they find a pi, they find a root 2, root 3. Those numbers are crazy numbers, and they are irrational numbers. Irrational numbers cannot be written in this form, all right? Rational numbers, another way to understand rational numbers is they are either terminating, decimal, or non-terminating but repeating decimal, non-terminating or repeating. Decimals. But irrational numbers don't work like that. Irrational numbers are like crazy. The digits to the right of the decimal point continue forever, never stop. And there's no pattern. There's no pattern. And those numbers are called irrational. And the rational numbers and the irrational numbers together make the real number set. Right? And I can give you a graph that shows the number system. So this is the whole number set. This is natural number set. I'm sorry. This is a whole number set. And then integer number set. And then rational number set. And then with irrational, you can see the box as the real number set. And inside the box, outside the circle of rationals, we have irrational. We can see this as irrational. So that's the real number set, number system. And this chapter, we expanded the system to complex number set. So as you can see, the real number set is just the one scale in a complex number set. The real number set, that complicated real number set is just the one scale, this red horizontal scale. And the complex number set include all the points in a two-dimensional space. Yeah, I did not spend too much time on this, right? Just want you to review the development of the number system. All right, so today we scheduled to cover section 2.2. Section 2.2 is about solving quadratic equations. And firstly, we need to know, what does a quadratic equation look like? And we need to know the standard form of a quadratic equation, because the first step, most of the time, the first step when you need to solve a quadratic equation is to rewrite the equation in a standard form. What's the standard form? This is the standard form. Okay, A, B, C are real numbers. A here is the coefficient of x squared. B here is the coefficient of x. C here is the constant term, is a constant, equals 0. In the standard form of a quadratic equation, the right side of the equation is always 0. We require A has to be non-zero. A cannot be 0, because if A equals 0, we do not have this term anymore. Then the equation is not quadratic anymore. Quadratic in algebra means degree 2. Quadratic in algebra means degree 2, all right? Degree 2. And any equation that can be written in that form is a quadratic equation. And there are 4 methods to solve a quadratic equation. 4 methods to solve a quadratic equation. And we are solving the quadratic equations in the complex number set. You might remember in Algebra Foundation 2, you have already learned solving quadratic equations. But at that time, you learned solving quadratic equations as an application of a polynomial factorization. You have learned solving quadratic equations by the method of factoring. At that time, you are not solving the quadratic equations in a complex number set. In fact, you are solving the equation in a rational number set. In a rational number set means if the equation has irrational solutions or even complex number set, not complex number as solutions, you cannot apply that method. Just to let you know, in this section, we are solving quadratic equations in the complex number set. And we need to know this conclusion, very important. Note, in the complex number set, a quadratic equation always has two solutions. Always have solutions and always have two solutions. Maybe sometimes the two solutions happen to be identical, but they are technically still two solutions. This is different from what you have learned in Foundation 2. In Foundation 2, if a quadratic trinomial is not factorable, at that time, not factorable means not factorable in the rational number set. Then the corresponding equation has no solution, right? But here, any quadratic equation has solutions in the complex number set. In the complex number set, we can solve any quadratic equations. They always have solutions, and they always have two solutions. Maybe sometimes the two solutions are identical, but they have two solutions. We just say they are identical, all right? I hope this is clear. So let me show you the four methods though. Topic number 6 here. We have the first question, solving by using factoring. That's what you have learned in Foundation 2. And the second method, solving using square root property. Third method, solving by using completing square technique. Method number 4, solving by using the famous quadratic formula. Okay, it's gonna take a little time. Be patient. The first method, solving by factoring. That method doesn't apply all the time. It only applies when the equation has solutions in the rational number set, when both solutions are rational numbers. So the application of this method is limited, right? Is limited, solving by factoring. Okay, let's look at the equation. The equation is negative 20x squared plus 2x plus 6 equals 0. Okay, and as you can see, the leading coefficient is negative 20. Leading coefficient refers to the coefficient of x squared. When we say leading coefficient, we mean the number in front of x squared. And we notice that number is negative. We do not like negative. Not just the leading coefficient is negative we don't like, we also notice the three coefficients in the quadratic trinomial on the left side. They have a common factor. Did you notice? 20, 2, 6, actually including 0. They are all even numbers. By the way, 0 is an even number. In other words, the four terms in the equation, term 1, 2, 3, 4, they have a common factor 2. Why don't we just get rid of it, right? All right. Now just get rid of the 2. We don't like the leading coefficient negative, so we are going to divide everything by -2. Even the equation is already in a standard form, but it's not simplified. So we should always observe, look at the equation before, figure out a way to handle the equation before actually start to solve it. And we notice we could get rid of 92, right? Let's do that. -20 divided by 92, positive 10, 10x squared. Positive 2 divided by -2, negative x. And this one, 93, and equals 0 divided by 92 is 0, right? And this is the same equation with the original equation, but looks a lot simpler. Okay, and how are we going to solve this quadratic equation with leading coefficient different from 1? I use the slide divide method to solve a quadratic equations with leading coefficient different from 1 in the rational number set. Okay, this method only applies when the equation is solvable in a rational number set. Well, let me show you how do I do that. We do not like leading coefficient different from 1. We like the leading coefficient to be 1. So we're going to slide it away, not far away. Slide 10 away and to be with the constant and create a new equation. The new equation is x squared. So since the 10 in front of x squared is slid away, there's nothing in front of x squared, right? So the coefficient of x squared becomes 1. The middle term stayed the same. The constant term was 93, but remember we push 10 over there, right? So 10 is going to multiply with 93. 93 times 10 is -30. Okay? And now this equation, the left side, is a quadratic equation with leading coefficient 1. Do you guys know how to factor it? Yeah, we are using solving by factoring method. More specifically, slide divide. It still uses a factorization technique. So we need 2 numbers. They multiply to -30, add up to -1. We need 2 numbers, multiply to -30, add up to -1, right? And the 2 numbers are -6 and +5. I think you should know how to do that. One of the announcements I posted is about watching my videos from Foundation 2. And I pointed out you need to know how to factorization for this course. So -6, +5, multiply to -30, add up to -1, right? And the two numbers in red, we're going to divide. So slide, we did a slide, right? Now we're going to divide. Divide the 2 red numbers by the original leading coefficient. Earlier we kicked it out. Now we brought it back. Divide by 10. And then simplify. Don't forget to simplify. Simplify 6 over 10 or -6 over 10. We have a -3 over 5. Simplify 5 over 10, that is half, right? +half. Okay, that's what we want. What we want is the right side of the equation 0. The left side of the equation has 2 linear binomials multiplied together. And in each parenthesis, we have 2 parentheses. In each parenthesis, we have x plus number and x plus another number, right? Do you see those two numbers in red? I can actually highlight them in yellow again, also, just to stress they are important. So -3/5, positive half, right? And the solutions are the solution set. The solution set of the equation is, it has two solutions. The first solution, 3/5. Second solution, -half. Look at this red number and highlighted in yellow. The -3/5 is the opposite, is a positive 3/5. That is a solution. And then look at here in the second parenthesis, we have half positive. Its opposite is -half. -half is also a solution. We found the two solutions. This topic is a big topic from Foundation 2. We don't have time to really go very deep. I have the videos. I hope you spend time to look at it. And a good news is, if you really suffer, really struggle with this topic, solving by factoring, it's okay. You know why it's okay? Because we're going to learn more methods, and you can just use other methods. Just to forget about this method. But I still had to cover it. So, and that's it. All right. Yeah. So the first method is solving by factoring, and that method only applies when the equation is solvable in a rational number set. What about this problem? 3x squared minus 9x equals 0. It is a quadratic equation because here degree 2, right? However, the left side is not a trinomial, it is a binomial. I think for this type of problem, we can quickly use solving by factoring. There's no need to use other method we are going to learn because this is just so simple. Let's see, the binomial is a quadratic binomial, right? And we actually also, we do not need to rewrite the left side as a standard form. We do not need to put a 0 here. Okay, we don't. We actually prefer there's no constant term, because left side, the two terms have GCF, which include 1x. So the two terms on left side, what's the GCF? The two terms on left side, 3, 9. The GCF of 3, 9 is 3, right? X and x squared, the GCF is x. I want to ask, do you guys agree the GCF of 3x squared and -9x is 3x? GCF is also a very, very important topic in Foundation 2. I also have the video in my video set. Some response? So far, so good?
Yes, I agree.
Okay, 3x. So if we factor 3x out, what's going to be inside the parentheses? Do you agree? Or if you are not sure, you can always double check by distribute, right? 3x times x, 3x squared. 3x times -3, -3, and -9x. So that's it, right? And technically, do you think we can get rid of the 3 here? It's not necessary, right? Because if we divide by 3, each side of the equation, if we divide by 3, 0/3 just 0, right? So the equation can be written as x times x minus 3 equals 0. And I can rewrite the left side as this. X times x minus 3 can be written as x minus 0 times x minus 3. All right? Same with earlier. I color this as yellow, highlight as yellow. And look at those two numbers I highlighted. Their opposites are, the opposite of 0 is 0. The opposite of -3 is +3. And those are the two solutions. solving by factoring. Solving by factoring. You want the right side be 0, left side as left side is a multiplication of 2 parentheses. In each parenthesis, in each parenthesis, you have variable x plus a number. In this case, we rewrote the left side as x minus 0, the number is 0, and x plus -3. So -3 is the number in the second parenthesis. And those two numbers, their opposites are the solutions. The opposite of 0 is 0, by the way. The opposite of -3 is +3. So the solutions are 0 and 3. Okay, for more details, I would recommend that you go to my videos and look at them. Second method, solving by square root property. Then we need to know what is the square root property, right? Let me give you the square root property here. The square root property. The square root property says if x squared equals a. A here, by the way, could be any real number, all right? Then x is plus minus root a, where a can be any real numbers. Means a could be positive, could be negative, could be 0. Okay. For example, if we know x squared equals 9, then by using the square root property, we have x equals plus minus, do not forget that, plus minus root 9. And we know root 9 is 3, right? So the two solutions are plus minus 3, positive 3 and negative 3. What if we have x squared equals 0, right? The right side, the a here, the right side, the number also could be 0. In that case, the formula, the property still applies. We apply the formula. We have x equals plus minus root 0. And we know root 0 is 0. So x equals plus minus 0. We know positive and negative 0 is 0. In this case, by the way, the equation has two solutions, but the two solutions are identical. The multiplicity of the solution 0 is 2. You don't have to worry about that. Just know when you think, oh, there's one solution, but actually it's two solutions. It's just the two solutions are identical. What if the number on the right side is negative? For example, x squared equals -16. Can you solve it? Yes, because we are solving in a complex number set. Again, we are solving the equation in a complex number set. Even earlier, the two problems, when we use the factoring method, we're still solving in a complex number set. Because the rational number set is a subset of the complex number set. It's just part of it, right? So as you can see, the equation x squared equals -16 is not solvable in the real number set. But again, we are solving it in a complex number set. And I also mentioned this formula, this property applies even when a is negative. A could be positive, could be negative, could be 0. It's okay to be negative. And the formula, the square root property still apply. So let's apply the square root property. We have x equals, so the base equals plus, don't forget that, minus, plus minus, square root -16. Okay, it's been a while. What is the square root of -16? What is the square root of -16? Square root of a negative number. When you see square root of negative number, do you apply that formula right away? Rewrite square root of -16 as the square root of 16i. And the square root of 16 is 4, so we have a plus minus 4i. Yes, this equation do not have solutions in the real number set, but in a complex number set, it also has two solutions. One solution is 4i, the other solution is a negative 4i. Okay, Those are just the warm up. Let's look at problems. This problem, 2n squared minus 13 equals 97. Okay, another problem before we do that. When do we apply square root property? When do we apply it? When to apply this method? When the equation has a perfect square and is easy to be isolated. For example, in this equation, we only have an n square. All other terms are just constants, right? So it's very easy to isolate the perfect square. Let's isolate it. The equation is 2n squared minus 13 equals 97, right? 1, 2, 3, 3 terms. And we can very easily isolate n squared on the left side. So let's do that by adding 13 first and cancel. So we have 2n squared equals 6, right? And then divided by 2, cancel. We have n squared equals 3, right? Yeah, n squared equals 3. And then we're gonna apply the square root property. It's very convenient because we have the perfect square isolated on the left side, and that doesn't take too much effort. The base of the square, this is the base of the perfect square, okay? The base of the perfect square equals plus minus root 3. Done. As a quadratic equation, it only have two solutions. We found the two solutions. The two solutions are root 3, negative root 3. Those two solutions are irrationals. They are not rational. They are not rational, so the factoring method doesn't work, right? Yeah, but the square root property method works perfect. Yeah, some of the questions in your Lumen belong to this type of problems. When the perfect square is very easy to isolate, and you can use the square root property. Some feedback? What do you think about this method? You only apply this method when it's convenient. And when is convenient? When it's convenient to isolate the perfect square, right? Any questions so far?
No questions, I understand it.
Okay, very good. Then try this one. This one, this equation is quadratic. How do I know it's quadratic? Because left side is 6t plus 12 to the power 2, right? If you expand it, it's 6t plus 12 times 6t plus 12. If you FOIL or whatever, or box method, you will see the highest degree is 2. So it's a quadratic. And this equation is not in the standard form, but it's totally fine. And actually, because it's totally fine because we can use the square root property to solve it very quickly. The left side is a perfect square already. You know, the left side has a perfect square isolated there. That's the ideal case for us to apply the square root property. The left side has nothing else but a perfect square. In this case, the perfect square has a base blue, the base is blue, and the exponent is 2, right? Okay, let's apply square root property. Let me write the square root property again. If x squared equals a, then the base equals plus minus root whatever on the right side. So we can apply square root property. The base, 6t plus 12, the base, the blue is the x in the formula. The blue equals, don't forget plus minus, square root of whatever the number on the right side, 121, right? And 6t plus 12 equals plus minus. We know square root of 121 is what? Do you remember? Square root of 121 Okay, if you guys remember that, next time I'm not going to scroll up, scroll down. You see 121 is one of the numbers. 121 is square of 11, right? Okay, let's go back. Square of 11, so 11. And from here, you are going to separate, right? 16 plus 12 equals positive 11. Or the logical connective is OR. 16 plus 12 equals negative 11. And then you solve the two linear equations separately. And you minus 12, you have 16 equals negative 1. And this gives you t equals negative 1 over 6, right? And this one, you minus 12, you have 16 equals negative 23. Negative 23. And then you divide by 6, you have t equals negative 23 over 6. Done. You found the two solutions, right? Not too much trouble. I don't think this is a lot of troubles. So square root property is a good method when the equation has the perfect square already isolated on the left side, like this format or this format. And square root property is very convenient. Okay, it's very convenient. That's the third method, right? Hold on, no, that's the second method. The first method, solving by factoring, only applies when the left side of the equation factorable in a rational number set. Second method is square root property, only apply when it's convenient to apply. Convenient to apply means the left side already have a perfect square isolated, or it's easy to isolate the perfect square on the left side. And the right side have to be a number, no x in it. And the third method we're going to learn is the completing square technique. And we don't really use this method to solve equation, but this is the technique we use to derive the famous quadratic formula. So here I'm going to derive for you, right? We have this perfect square trinomial. We have the perfect square. Sorry, we have this quadratic equation. We have this quadratic equation in a standard form. Ax squared plus bx plus c equals 0. Leading coefficient a is non-zero. Okay. We want to use a square root property to solve it, but we do not have a perfect square, so we're going to complete perfect square. This is what we do. I'm going to rewrite it, make it bigger. Ax squared plus bx plus c equals 0. A is not 0. Since A is not 0, I can start with divide everything by A. Right? Since it's not 0, so it can stay on the denominator. Cancel. So we have x squared plus b over ax plus c over a equals 0. 0 divided by a is also 0. And then I'm going to get rid of the constant term from the left side. In other words, move the constant to the right side. Then we would have x squared plus b over ax equals negative c over a. All right? And then I'm going to add a number in the cell. I'm going to do the same thing to the right side to keep the equation unchanged. What's going to be the number in the cell? The number in the cell is going to be, we actually consider that. We already covered this before. When we learned circle, when we learned how to convert the equation of a circle from general form to standard form, we learned this technique. So in the cell, we are going to have the square of half of the coefficient of x. Okay, what's the coefficient of x? Coefficient of x is b over a. Coefficient of x, b over a. What's half of it? B over 2a is half of it. And then to the power 2. And that is b squared over 4a squared. All right? B squared over 4a squared. So we have b squared over 4a squared. We're going to do the same thing, b squared over 4a squared. Yeah, the square of half of the coefficient of x. Coefficient of x is b over a. Half of it is b over 2a. Square of it, b squared over 4a squared. Okay. And the left side can be made as a perfect square. So the left side right now is a perfect square trinomial. And we can write that trinomial as a square of a binomial sum, x plus b over 2a. On the right side, we have negative c over a plus b squared over 4a squared. Let's spend a little bit of time to simplify the right side, okay? Let's spend a little bit of time to simplify this part. Negative c over a plus b squared over 4a squared. We are adding two fractions. We need them to have the same denominators. They do not have the same denominators now. We need to make them do. So the first fraction, we are going to multiply both top and bottom by 4a. Okay? Then the first fraction, numerator is negative, by the way. Numerator is 4ac. Denominator is 4a squared. And then plus b squared over 4a squared. Now they have the same denominators. We can keep the denominator, 4a squared, and solve the top, negative 4ac plus b squared, or b squared minus 4ac all over 4a squared. To the right side, I need more space. So the right side of the equation becomes left side x plus b over 2a to the power 2. Right side becomes b squared minus 4ac all over 4a squared, right? And now we finally have the ideal form we want in order to apply the square root property. The square root property, all right? Square root property. On the left side now, we have a perfect square isolated. This is a square yellow, and the base, this is the base blue. So the base blue, x plus b over 2a, by the square root property, is going to be plus minus square root of the number on the right side. B squared minus 4ac over 4a squared, right? And then continue to simplify. And we minus b over 2a from each side. We have x equals negative b over 2a plus minus square root b squared minus 4ac over 4a squared. And that can be written as, I can simplify it this way. Negative b over 2a plus minus square root b squared minus 4ac. We use the square root property of square root, not square root property, and square root 4a squared, and that can be written as square root b squared minus 4ac. Square root of 4a squared is 2a. Technically is a absolute value of a. Yeah, technically it's supposed to be absolute value of a. Let me think. Then we have to, so we can assume a is positive, and then we assume b is negative and do it again. I don't think it will matter too much. So here I'll just write 2a, and then we would have the two parts have the same denominator, 2a, and then b plus minus root b squared minus 4ac. And that's the famous square root, that's the famous quadratic formula. That's the famous quadratic formula. X equals negative b plus minus square root b squared minus 4ac all over 2a. And it's very useful. You should spend time to memorize it, especially when you struggle with factoring method, and you should use this method. How to use it? How to use it? If we have a quadratic equation, ax squared plus bx plus c equals 0, you identify what is a, what is b, what is c, right? And you plug it in. That's how you use it. Very, very simple. There's a song. If you want to learn, I can sing for you. It says x equals negative b plus minus big square root b squared minus 4ac all over 2a. In YouTube, we also have many teachers. They make their own song and with guitar, very fancy. And you can find one and whatever the way to try to memorize it. Okay? And this part, I want to point it out. This pink part, the stuff under the square root, very complicated, right? It's not very convenient to plugging in, and it plays an important role. And actually, we have a name for it. I use delta, okay? I use delta. It's called a discriminant. Delta equals b squared minus 4ac. Since you are taking my class, try to use my notation. It's very convenient. So I would, to apply the formula to solve equation, I would firstly identify values for ABC, and then figure out what is delta, and then figure out what is delta, and then plug in to the equation, the formula. All right? Let's apply it. Solving by using the quadratic formula. Solving by using quadratic formula. Quadratic formula is important also because it's simple, right? The only challenging part is you need to memorize the formula. And as I said, there's a lot of songs you can try to help you to memorize. And it applies to any type of quadratic equations. And you just need to rewrite it in a standard form to identify ABC. In this equation, 4x squared minus 3x minus 6 equals 0. I can write a formula for the standard form right below the equation. Then you can compare and help you to identify what is A, what is B, what is C. A, B, C. What is A, guys?
4.
What is B?
-3.
Thank you. It's a negative. Appreciate that. It's important you include the sign. All right, very important. And C is a -6. Perfect. And now we'll do the delta. Do you guys remember what's the name of delta? Delta here. Hello? It's discriminant. All right, discriminant is b squared minus 4ac. Okay, let's plug it in. Yeah, how do we plug? How do we plug it in? This how do we plug it in? If you are still struggling with that basics, do this. Use parentheses to frame those letters, and then let those letters retire, and then you put the numbers of the letters in it. Remember, this is B. B is 93, so put a 93 here. A is 4, so put an A here. Put a 4 here. Yeah, A is 4, so put a 4 here. C is 96, so put a 96 here. Do not rush. Why maybe some of you messed up those evaluation, very simple thing, because you rush. You want to get it done quickly. You want to get it done in one step. A lot of things you cannot get it done in one step. A lot of things in higher level courses, it takes a long process. If you go to master's degree program or even doctoral program, one thing probably take you 1 year. My doctoral dissertation took me almost 2 years. The one thing, one project. So be patient. Square of 93, 93 times 93 is a positive 9. Be very careful. You do not have a negative 9. You have a positive 9. Yeah, those are simple. That's actually the thing I worry about. Those are things from foundation. And here, 94 times 4 times 96. The three numbers have 2 of them are negative. So I don't know if you can see we're going to have a positive thing, positive number there. And positive 4 times 4 times 16. Sorry, 4 times 4 times 6. So 16 times 6, I think it's 96. 16 times 6. 96, right? Positive 96. And 9 plus 96 gives us 105. And let me double check. 16 times 6, I believe so. I don't mind you use calculator, by the way. 16 times 6, 96. 96 plus 9, 105. Yeah, that's correct. So the discriminant is 105. And the square, the famous quadratic formula is x equals b plus minus square root. You can sing the song again, right? The big square root. Under the square root, you have the delta, but we already have the value found. So all over 2a. And now let's plug it in. B is -3. Negative b, the opposite is a positive 3. That's somewhere people make mistakes for a reason. Maybe because negative is kind of confusing. Think about opposite. Instead of confuse yourself with negative, think about opposite. Negative b, this part, is the opposite of b. B is -3. Its opposite is a positive 3. Plus, minus, square root of delta, which is 105. Let me rewrite this. Plus, minus, square root 105 over 2a. A is 4. A is 4, we got twice of a, 8. Right? Okay. We have a square of 105. We need to simplify it. 105. The last digit of 105 is 5, right? So we know 105 is divisible by 5. Let me get a calculator. $105 divided by 5, 21. Okay, so we can write root 105 as root 5 times root 21, right? And root 21 is root 3 times root 7. So root 105 is root 5 times root 3. There's nothing we can do, right? There's nothing we can simplify. There's nothing we can simplify this square root. The square root is already simplified. That's how we know. We analyzed. We figured out there's nothing we can simplify. So it's going to stay like that, all right? And we got the solutions. You can leave this, I don't mind. The reason the structure is important in algebra is because of this. Because the quadratic formula has this mini Mickey Mouse structure. Left ear, right ear, and head. You can just answer. The first solution is 3 plus square root 105 over 8. And another solution is 3 minus square root 105 over 8, right? That's it. That's it. So practice another one. Use the same method. Square root quadratic formula method. Quadratic formula method. 2x squared plus x plus 1 equals 0. Standard form right under, then you can compare, help you identify ABC. A, 2, B, 1, C, 1. Once we have ABC, we are going to find delta, which is b squared minus 4ac. B is 1, put it here. A is 2, put it here. C is 1, put it here. And then evaluate. Square of 1 is 1. And this is just a 1 negative. 4 times 2 times 1 is 8. And we have -7, right? -7. Yep, okay. And then the famous formula, x equals -b plus minus big square root delta, right? All over to A. And let's plug in. B is 1. So negative B, the opposite of B is -1. Plus minus square root of -7. Over, all over 2A. A is 2. 2A is 4. And so that's it. But not done yet, right? Because we have a square root of -7. When we see a square root of negative number, right away apply the formula. We can write root -7 as root 7i. And root 7 is already simplified. And as you can see, left ear, right ear, head, nothing can cancel. So it's going to be like that. One solution is going to be -1 plus root 7i over 4. I'm okay with this. We're going to look at the lumen to see what's the requirement. If the problem requires you have to write the result in a standard form, you're aware this is a complex number, right? Non-real complex number. So then you would have to. You just need to use -1 over 4, -1 over 4, and then plus root 7 over 4i. So this is a complex number in a standard form, right? Real part, -1/4. Imaginary part, root 7 over 4. Imaginary unit is I. And another solution, -1 minus root 7i over 4 is always its conjugate. Yeah, if a quadratic equation has two non-real complex solutions, means there's an I in it, then the two solutions always are conjugate of each other. It's -1 over 4 minus root 7 over 4i. Remember conjugate? A plus bi and a minus bi are conjugate. All right? Two complex numbers are conjugate if they have the same real part but opposite imaginary part. So this equation do not have real solutions, but they have two non-real complex solutions. In the complex number set, any quadratic equation is solvable. Always have two solutions. Okay. Next topic. The geometric significance of the solutions of a quadratic equation. All right. Let's see, we have the quadratic equation. Yeah, I need more space here. Let's put a page break here. This is not included in our book, but I think this is important to know this. Let's say the equation is ax squared plus bx plus c equals 0. All right. A has to be non-zero. It has to be non-zero. And the delta is b squared minus 4ac. All right. And if we let f of x to be the left side of the equation, ax squared plus bx plus c, then the graph of f of x is a vertical parabola. Either opens up or opens down. A parabola could open to the right or open to the left, or even rotate it, like open to top left. We don't go that far yet. So function f, this quadratic function, the graph is a vertical parabola, either opens up or opens down. Okay. I mentioned here we're gonna have six graphs. The first one, 1, 2. Do that again. Sorry. 1, 2, 3. And another 3. Okay. The top 3, I'm going to make A positive. The first graph, leading coefficient is positive. Delta is positive. Do you guys remember what is delta? Discriminant. It is the base square minus 4ac, okay? Then the graph of the function f of x, which is the left side of the equation, is going to be like that, like this, something like this, okay? And those two x-intercepts are solutions. It has two real solutions. If A is positive, but delta equals 0, then the graph looks like this. Delta equals 0, negative b over. So if that negative b over 2a, yeah, this is the solution. Negative b over 2a. It has one real solution, but again, in fact, it's two solutions, but they are identical. Two identical solutions, all right, if delta equals 0. If A is positive, delta is negative, then the graph should look like this. There's no x-intercepts, so no real solutions. The equation has no real solutions. No real solutions means it's gonna have two imaginary solutions with I in it, okay? And then the other 3 graphs, they have A is less than 0. And this one, delta bigger than 0. This one, delta equals 0. This one, delta is less than 0. So when the leading coefficient is negative and delta is positive, it's like this. It has two different real solutions, all right? It has two different real solutions. When A is less than 0, delta equals 0, it looks like that. It have two identical real solutions. If A is less than 0, delta is also less than 0, it looks like this. There's no real solutions. Okay? Does that help to organize the cases of the solutions of a quadratic equation? You can understand this as 3 categories or 3 cases. If delta is positive, then the equation has two different real solutions. If delta equals 0, then the equation has two identical real solutions. If delta is less than 0, then the equation has no real solutions, but it will have two non-real complex solutions. And those two non-real complex solutions must be conjugate of each other. Okay, so let's look at the next topic. We have 5 minutes. The last topic is regarding a theorem. It's actually not the whole theorem, it's part of it, because we only consider a quadratic equation when leading coefficient is 1. It's called Vieta's theorem. Basically, it says in the complex number set, the equation has two solutions, right? The sum of the two solutions is C. The multiplication, my bad. The multiplication of two solutions is C. And the sum of the two solutions is the opposite of B. Let me write it down. Say x1 and x2 are the two solutions of x squared plus bx plus c equals 0. Then the two solutions multiply to the constant term. And the two solutions add up to the opposite of the middle term coefficient. This is the content. It's part of the theorem, but it's enough for us. Yeah, let's look at it. In a complex number set, any quadratic equation has two solutions, right? And we assume we only consider the quadratic equation with leading coefficient 1. That's important. We only consider a equals 1 here. Okay, we only consider a equals 1. Then the two solutions must multiply to C, which is the constant term on the left side of the equation. And the two solutions add up to the opposite of B. B is the coefficient of X. And let's apply this theorem. The problem says, suppose the quadratic equation x squared plus bx plus c equals 0 has two solutions, h and -1. What are b and c? By applying the theorem here, we know the two solutions multiply. Yeah, a and -1 are the two solutions. They multiply to c. They add up to the opposite of b, right? Well, then we should be able to find out what is b, what is c, right? A times -1 is -8, so c is -8. 8 plus -1 is 7. 7 is -b, so b is -7. Do you see that? Response?
Yes, I understand.
Okay, very good. A lot of things takes memory. You do have to memorize a lot. Let's do this one the last, okay? Let's do this one. Same idea, same with earlier. The two solutions, 99 plus 2i, 99 minus 2i. As you can see, they are conjugate, right? They must multiply to C and add up to -b. Let's do the addition. Let's do b first, it's easier. Let's remove the two parentheses. 99 plus 2i negative 9 minus 2i equals negative b. 2i, negative 2i cancel. Negative 9, negative 9, negative 18. So b is 18. B is 18. That one is easy. For the multiplication one, if you know the formula, it's going to be easy. If you don't know, we proved a formula last class. A plus bi times a minus bi equals a squared plus b squared. A is the real part of the complex number. B is the imaginary part of the complex number. We only take the positive one, the absolute value. So as you can see, the real part, negative 9, right? And the imaginary part, 2. And this one's negative 2, but take the squares to do the same thing. So we take the positive one. So multiply them together, negative 9 plus 2i, negative 9 minus 2i. By using the formula, we should have the real part, negative 9 to the power of 2, plus the imaginary part to the power of 2. Square of negative 9, 81. 2 square, 4, 85. And that's C. And that's it. Regarding application of a quadratic equation, we would have to wait for the next class. I hope everything is clear for today.
Yes, I understood it.
Okay, very
I
good.
got everything. Wow.
Yeah. Try to work on your lumen as early as possible. Just to let you know, every assignment has a prerequisite. For example, if you want to do your assignment 1.7, it requires you have to pass 1.6 with 75% or above. If your score in 1.6 is too low, it will not let you to start 1.7. Just in case you haven't noticed that yet, there's a prerequisite for each assignment. All right, guys. Let me know if you have any questions. You can email me. Today is Tuesday. I'll see you on Thursday. Bye-bye.
Bye. Thank you.
Have a
You're
good
welcome.
one.
You too. Bye-bye. Green chain sharing has stopped. Lisa, do you have any question? Okay.